So in this video, we will see about B tree. So B tree is a kind of binary search tree. So BST, that is binary search tree. So everyone knows what is binary search tree. So in the binary search tree, this is each node can have at most two child. And these elements are organized in a particular order. So that left child, the value should be less than the key value of its parent. And the right child value should be greater than the key value of the parent. Okay. And so actually how these moves are implemented means each node have two pointers. So this is left pointer and this is right pointer. And here the key variable k will be stored. And another property of this binary search tree, so each node can have only one key variable. And each node can have at most two child. So this property is it even in a binary search tree. So each node can have only one key value and each node can have at most two child. Now we will come back to this B tree. So as I already told you, this B tree is a kind of binary search tree. So that means the values are stored in a particular order, very similar to the binary search tree. That means the similar values will be stored in the left child and the greater value will be stored in the right child. But what is the difference between this B tree and linear tree is the number of keys and the number of child that you can have. So a B tree, so each node can have n number of child and m minus 1 key values. So in a binary search tree, each node can have only one key and at most two child. Say in a B tree, each node can have at most n number of child and each node can have at most n minus 1 key values. Now, how we actually represented. So, suppose if m equal to 4, suppose we are going to create a B2 with the value m equal to 4. So that means each node can have at most 4 child and each node can have 3 key values. So In a binary search tree, so while looking at the binary search tree structure, we also can identify so that the number of pointers in the node is true. So one pointer is for left side, another pointer is for right side, and then key value. So here is n equal to 4 is so m minus 1 key values. It can have m minus 1 key values, and each node can have m number of pointers. So this is one of the important things that you need to remember. So in the binary system, one key and then two pointers. So in B3, if that n equal to 4, suppose we need to use some m value, that m indicates the maximum number of child a node can have. And each node can have n minus 1 keys and m pointers. So I will explain how it can be, that node can be represented. Suppose if m equal to 4, m equal to 4 means, so m equal to 4 means, so each node can store 4 key values. For example, key 1, key 2, key 3, and key 4. Sorry, we can only have 3 key values. M equal to 4 means then only 3 key values. Suppose K1, K2, K3. And 4 pointers is, these are the 4 pointers. So this is one pointer, this is another one, this is one, and this is 4. So if n equal to 4, each node can have 3 key values and 4 pointers. So almost 3 key values. If it has 3 key values, means this will have 4 pointers. Suppose their particular node have only 2 pointers, 3 key value means this will have 3 pointers. Suppose we have only 1 key values means it will have 2 pointers. Okay, so it can have key values from 1 to m minus 1. And this particular pointer points to another node, and this node also is the same kind. That means it also can have maximum m minus 1 key values. And all the key values should be less than this key value. So this, all the keys in this particular node should be less than k, and this pointer points to another node of the same kind, and all the keys in this particular node should be in between k1 and k2. Means it should be greater than k1 and less than k2. So here also same. So all the keys should be between k2 and k3. And here this pointer points to another node of the same kind, and all the keys in this node should be greater than k3. Okay. So apart from this, another important property that we have to maintain in B3 is this balancing. It's balancing property. So what is actually this balancing? So we have ABL tree. In the ABL tree, we have balancing factor. So the same way, the B tree is also a balanced tree. Like the BST is a set tree. So this tree is this particular data structure is used for efficient searching. As well as this tree should also be a balanced one. So how to maintain a balance in here? So all the leaf nodes. So all the leaf nodes should be in the same level. So this is another important property in BG. So all leaf nodes should be in the same level. So in binary search tree, we don't maintain this particular property. So I will explain this with an example in a binary tree. Suppose in the binary tree, first we start from one value 10. And then I'm going to insert another value that is 20. So now it has only one leaf node 20 and it is in the level, so level 1. And then now I'm going to insert another leaf node, another node that is 15. So 15 should be inserted there. So this is greater than 10, less than 20. So now it has only one leaf node and this is not in the level 2. Now I'm inserting another node 25. So this is greater than 10 and greater than 20. Second also will be in the right side of 25. Now I need to, so now we have in this particular state, we have two leaf node, both the leaf nodes in the same one. So suppose I'm going to insert another node 22. So 22 greater than 10, greater than 20, but less than 25. So in this particular level, so we have two leaf nodes. This 15 is a leaf node and this 22 is a leaf node. While 50 is in level 2 and 22 is in level 3. That means in a binary search tree, at any point of time, we inserting a node. So the leaf nodes, we can have a leaf node at the different level, but it should not be maintained in binary, sorry, B tree. So while inserting any node in the B tree, we should maintain that all the leaf nodes should be in the same level. Okay. So as of now, you need to understand three things. So B3, each node can have almost m child and n minus 1 key, and all the leaf nodes in the B3 should be in the same level. So in order to maintain that particular dimension property, so while creating or inserting a B3, we have to maintain some rules. Okay, so rules in B3. So the first rule is, so all internal nodes should contain m by 2 minus 1 keys. Okay. So all the internal nodes should contain m by 2 minus 1 keys. For example, if m equal to 4. So while inserting nodes into the B tree, so apart from the root node and leaf node, apart from this root and leaf node, all the internal nodes should contains 4 minus 2 minus 1. So this is equal to 1. So contains one key. Suppose m equal to 8, then 8 minus 4 minus 1 is equal to, so 8 by 2, sorry, not 5, m by 2. So 8 by 2 minus 1 equal to 3. So all the internal nodes will contains, at least contains 3 things. Okay? So this is the first rule that we need to maintain. All the internal nodes will contains equal to minus 1 things. So apart from the internal node, leaf node, so contains one node. So almost one node. So for the leaf node, so because we need to start our implementation, so that VTs can be created first by creating a root node. So initially root node is empty, and then we are first going to insert first node, only one key, and then one by one we will add keys into the root node. So this rule is not applicable for the root node, as well as in the leaf node also. The leaf node also can contains only one key. So only for the internal nodes, each internal node should contain at least 1 by 2 minus 1 keys. So if n equal to r means is n by 2 should be the values, C values will be taken. Suppose if n equal to 3. So 3 by 2 is equal to actually 1.5. So it will not be 4, it should be CO2. So 2 minus 1. Okay. So it should be, you have to remember this thing. So, so first thing, m number of child and m minus 1 key, and all the leaf nodes should be in the same level. And while inserting a node into the B tree, all the internal nodes should contain at least n by 2 minus 1 key values. And if the maximum number of key values can be stored in a single node is n. And the maximum number of pointers in each node is n plus 1. Okay. So these are the things that you need to remember. Okay. Suppose while inserting any node into a B3D, so I already told you because only you can be able to stay only n minus 1 keys. Okay. Suppose we have this, I will explain it in an example. So we need to store these 4 values, and the n value n is equal to 4. So n equal to 4 means each node can have at most 4 child, and each node can have at most 3 keys. So instead, so and then one more important thing we need to remember is that B trees can be created in bottom up method. So bottom up method. So this is actually B tree. B tree. So should be created in a bottom up method. So we already know that BST, binary search tree. So actually the binary search tree is created in top down method. So actually, what is the top 10 means? Initially, the root node is created in the top level. So once the root node is filled, that means the root node is created, and the next node will be created in the bottom level. So when this particular level is filled, the next two nodes will be created in the bottom level. So this is actually top down, but in beach is so first you need to start from the last level. So in the last level now we fill all the M-1 keys. Once this particular node is filled, M-1 keys are filled, then next two keys will be created in the top level. So and then on the top level, I am going to fill all the child. Suppose there is same number of child, I am going to fill it. So once this particular level is filled, then next two nodes will be inserted or created in the top level. So in this way, this is actually called bottom up approach. Okay. So binary search tree that is created using top-down approach, and in the B tree this will be created in bottom-up approach. So now I will explain in a single example. Now I need to insert this three keys. Okay. So and then m equal to 4. So m equal to 4 means the number of keys that can be stored in each node is 3. So first I insert the value 10. Now in this node 20 can be inserted. So I insert 20 and 30. So 30 also can be inserted because m equal to 4. So m minus 1 equal to 3. So 30 can also be inserted. Now I need to insert 40. So now when I try to insert this 40 into this node, the 40 cannot be stored. That means this condition, when I try to insert 40, overflow occur. This condition is called overflow condition. Okay? So when there is an overflow occur in a node, then we need to do a split up operation. So split up. So we need to split this particular node in a other manner. So how to split? So when I try to insert this 40, so actually this is the value in the particular node, but this value cannot be filled. So I'm going to split this node into two nodes. So this is actually left subnode and this is right subnode. Okay. So now I have two nodes. One node 10, 20, another node 30, 40. And then I can either select the maximum value in the left subnode. So this is left subnode and this is right subnode. I can either select the maximum value in the left subnode or the minimum value in the right subnode. Okay. So for this split of operation, we can select either of these two. Now I select this minimum value in the right subnode. And I'm going to add this value into the parent of this particular node. Now this node don't have any parent. So I'm going to create a separate parent. That means for this node, I'm going to create a parent node. And now the parent node only contains one value 30. So and then now already we have splitted two subunits. One is 10, 20, and another only contains 40. So I already told you. So this node contains only one key. So two pointers. Now this is a parent. There's two child. Now we need to link it. So run to the property of V3, wisdom and complete or resident with that is key 30. So it should be linked to this particular point. When this 40, this is greater than this 30, so it should be linked to this particular point. Okay. So this process is actually called the split up process. So while inserting a value, we need to follow this approach. So that means bottom approach. So initially, in the bottom level, we need to fill the node. And if any node that overflow occurs, then we need to do this split of operation. So they are split that node into two nodes, left subnode, right subnode, and then do this split of operation. So this is the way we need to insert a node into the region. Okay, so I will explain one example. Now, suppose we are going to insert these values 10, 20, 50, 60, 70, 80, 30, 35. Five, and then 50. This is the values by which we are going to create a V2. And remember, we are equal to 4. Okay. So this is the values that I'm going to insert. Okay. So now I just erase it and then I will insert the step by step. So initially, so we need to insert 10. So since n equal to 4, we can insert up to 3 keys in a single node. So first I insert 10 and then I can insert 20 in the same node. In the next one, I can insert 40 in the same node. Now there is no overflow. Now I'm trying to insert next node to be inserted is 50. So I'm trying to insert 50. While inserting 50, so this particular node will overflow. So I am going to split this node into two halves, two summers. So 10 and 20, 40 and 50. And I'm selecting this 40 and I'm going to make 40 as a root node. So now after it of how it will becomes, so 40. 40 will become the root node. From them, we will split two from this. The node contains two key values 10 and 20, and another node contains only one key value 50. Okay. So now 40 becomes code, and this node will be left. We will find it with the left pointer of 40, and it will be pointed with the right pointer. So next, I need to insert the key value k equal to 16. So start from the root node 68 greater than 40. So it will be inserted to the node which is pointed by this particular pointer. So right pointer. So the right pointer, there is one node, already have one node, and that node contains only one key value. So now, so maximum 3 key values can be stored. So I can store this 60 in this particular node. Okay. So the next two key value to be stored is 70. So let's take key value 70. So I compare 70 with 40. So for 70 is greater than 40. So it should be inserted to this particular node. So this node contains only two values. So maximum 3 values can be stored. So 70 node can be stored here. So this main contains 50, 60, and then 70. So now next key value will be inserted is 80. So 80 is greater than 40. And while I'm trying to insert this 80 into this particular node, we will plot that. So as usual, so I am going to split this into 2. So 50 and 60 will be one subnode, 70 and 80 will be one subnode, and I'm selecting this 70, and I am going to add this 70 to its parent. So its parent node contains only one. This is this part is its parent node, and it contains only one key. So this 70 can be inserted here. So now how it changes means, so now this 70 I'm going to add, so this 70 is added here. So I'm instead of this simple node, now it is split into two layers. So one node contains two key values 50 and 60. Another node contains only one key value, that is 80. So after this, we need to change the pointer. So I already told you. So this contains two key values. So it should have 3 pointers. So this 10 and 20 will be pointed by this pointer, and 80 is greater than 70. So this should be pointed by this pointer, and 50 and 60. So this between this 40 and 70. So this should be pointed by this pointer. Okay. So next I need to insert 30. So 30, while I'm trying to compare with that report that is less than 40, so it should be inserted in this particular. So it contains only two key values, so 30 can be inserted. So 10, 20, already there is 10 and 20. Now I'm going to insert 30. Now I need to do any split up operation. So after 30, I need to insert 35. So while inserting 35 should be inserted in this particular. So 35 is less than 40. So we should be inserted in this particular node. So, but I try to insert this node also at here. So, as usual, I'm going to do a split of operation. So, this is left subnode, this is right subnode, and I'm selecting this 30 and I'm going to move this 30 to the parent. So now this is the parent of this 30, this node. So already that parent contains only 2 key values. So now this 30 also can be added into the parent. So now this parent actually changed. So initially it contains 40 and then 70. Now I need to insert 30. So while inserting, no, it should be inserted in sorting order, means the ascending order. So first there will be then 40, then 70. So and then since here is 3 key values, so 4 number of pointers. This pointer 1, pointer 2, pointer so this is pointer 1, this is pointer 2, this is pointer 3, and this is pointer 4. Okay. So now this particular node is split into 2 nodes. So one is contains 10 and 20. And this contains only one value, 35. So now I need to change the pointer. So this node will be pointed by this pointer, and this 35 is between 30 and 40. So it will be pointed by this, and 50 and 60 is between 40 and 70. So it will be pointed by this pointer, and 80 there's no change. So after 35, we need to insert the next key value will be inserted 5. So 5 is less than 30. So it should be inserted in this node. So this node contains only 2 keys. So the third key can be inserted. So now, so already it has 20, 10 and 20. Now I need to insert 5. So while inserting, it should be inserted in the container. So 5. Then 20. So the next node to be inserted is 15. Okay. So 15 should be so less than 30, and it should be inserted in this particular node. But while inserting 50, it begins overflow. So maximum number of nodes is keys can be stored is 3, but now it begins 4. So as usual, 15. So the 15 should be inserted between 10 and 20. So 5, 10, 15. And we split this into 5 and 10 left, 15 and 20 becomes right subnode. And I am selecting this 15. Okay. And then I move this 15 to its parent. So now the parent of this 15 is this root node. But this root node already contains 3 keys. If you try to insert this 15, now the number of keys will become 4. So which should not be allowed. So if you perform the split of operation, Now the child for the root also it becomes over. So now the root 2 we need to perform split off. So now I'm trying to insert 15. So already there are 30, 40, and then 70. So I'm going to perform this. 15 and 30 are the left subnet, 40 and 70 are the right subnet. I'm selecting the minimum value is 40. Now this 40 is going to be the parent of this node. So I will explain this particular concept first. So now 40 will become the parent, and already that node is split into two subnodes. So one subnode contains values 50 and 30. Another subnode contains the value 70. Now, first in this level, I'm going to update the pointer. So 15 and 30 will be pointed by the left pointer and 70 will be pointed by the right pointer. And after that, so we need to insert this node. So already 5, 10, 20, it has been split up. So it has been split into two nodes. 5, 10 is a left node and 20 is a right node. So now I need to insert two nodes. I need to, so 5, 10, 5 and 10 will be 1 and 20 is another 1. Now I'm going to update this level pointer. So 5 and 10 are less than 15. So it will be pointed by this. And 20 is in between 15 and 30. So it should be pointed by this pointer. And 35 is greater than 30. So it should be pointed by the right pointer. That will be a good idea. Right? And then this 50 and 60, this particular node, it is less than 70. So it will be pointed by the left pointer of 70. And 80 is greater than 70 and it should be pointed to the right pointer. So this 40, this 40 is the parent of these two nodes. 50, 30, this is one node, and 70, this is another node. So this 40 is the parent of these two nodes. So these nodes should be linked with the 40. So 15 and 30 are less than 40, so it will be pointed to the right pointer of 40. And 70 is greater than 40, so it should be the right pointer of 70. Okay. And these two, three nodes are the child of this particular node, 15 and 30. So these three nodes should be linked with this particular node. And these two nodes are child node of 70. So it should be linked with this 70. Just perform the split up operation, and according to the values that are stored in each node, we can able to update the pointer. Okay. So finally, this is the actual V3 after implementing all this keys. Okay. So this is about insertion of the V tree. So first try to understand this insertion concept. So once you understand, and then we will upload the video for relation in V tree. Thank you.